Pete Shadbolt is the co-founder and chief strategy officer of startup PsiQuantum. PsiQuantum is building a large-scale, general-purpose silicon photonic quantum computer. And we're going to talk about some of the manufacturing challenges and political and funding hurdles that quantum will need to overcome to become a reality. Pete, welcome. It's great to have you with us today.
Hey, Amit, how are you doing? Great to see you.
Thank you. So, Pete, I mentioned the path to reality. What are the critical steps along this quantum computing path to reality?
Yeah, so I think the reality with all approaches to quantum computing is that they're coming out of university research groups. Quantum computing has this association with crazy materials, atomic scale fabrication, millikelvin temperatures, these kind of science fiction like devices and operating environments. And those inevitably start out somewhere in a university. And, we're no different. We spent 15 some years in the university in the UK building and testing small quantum computers. That was a fantastic time for me. We were taking single photons and putting them into silicon chips really for the first time. And that the sort of thing that kept me up at night at that point was, what's going to happen? Are these photons going to behave themselves? Can we entangle them? Is there going to be some crazy physics? All the time we understood something that's been understood about quantum computing for 20 some years, which is that ultimately you're going to need error correction. And therefore you're going to need millions of qubits if you want to deliver on the tremendously exciting, commercially valuable applications that we're all excited about. And when I was in the university, there was sort of a wave of enthusiasm for the idea that you might get something done with a small quantum computer. You mentioned quantum supremacy, and there was a period of time, I think, where people were optimistic that you might run commercially valuable applications without error correction. But I think that time is coming to an end, and people are recognizing again that we need something that is so much larger and so much more mature than the small scale experiments that we have today. And so when we founded the company, it was with the understanding that yes, you need 1 million qubits, yes, you need error correction. And of course, that can be a pretty daunting prospect. And certainly if you are building it the same way you would build a science experiment, that's going to take you a very, very long time to build a system like that. I think the idea that we've been strong proponents of for a long time has been that, of course, 1 million is a big number, and certainly for a scientist, it's a big, scary number. But there is an industry, the semiconductor industry, which has been the beneficiary of $1 trillion of investment over the last 50 years or so, that routinely works, a miracle of putting 1 billion transistors in your pocket. And so our approach has been to say, we need to take this, crazy science fiction technology of quantum computing, and we need to figure out how to leverage the tools and the manufacturing processes that allow us to build, very, very large numbers of devices for our conventional electronics, if we want to have any hope of delivering on the promise of quantum computing, in my lifetime, really. For us, the journey has been very much about getting out of the mode of science experiments and building hardware that is at a different level of maturity. Does that make sense, Simon?
Yeah, that makes perfect sense. And there are lots of different ways to build a quantum computer, as you hinted at, from superconducting to photonic to, diamond-based to NMR, and hundreds of different types that we don't really have time to get into today. And the favored approaches have changed over the years. Do you think the field as a whole is crystallizing around this idea that you talked about, that these devices need to mesh well with existing production lines, with existing technology, if they're ever going to be practically useful?
Yeah, that's right. So you're absolutely right. There's a ton of different ways to build qubits, using all sorts of different exotic pieces of physics. And I've worked on a couple of them myself, and it can be really confusing, right? And of course, everybody wants to know which is the best qubit. And the reality is that um, you can, of course, go and compare these qubits and look at the various pros and cons. In fact, I would say that today everybody can build a qubit, and those qubits are just fine. Whether it's superconducting qubits, quantum dots, or photons as we use, everybody is successfully building small systems of qubits, and there's nothing really wrong with them. They're fine. We can argue about the pros and cons. I think to your question about the shift in the industry, what you're seeing is people getting over that initial proof of principle and starting to really take seriously the question of how are we going to get to scale. And in that context, you can see very profound differentiation between these different technological approaches. And it's not really about the usual characteristics that we think of. What's the coherence time of the qubit? What's the single qubit gate fidelity or 2-qubit gate fidelity? It's much more about these less quantum characteristics like manufacturability, cooling capacity, control electronics, connectivity between qubits. There's nothing particularly quantum about these things, but these are the scaling obstacles that really stand in the way of a big system, and that's where you can clearly see differentiation between the technologies, I would say.
Those things are all very expensive to implement. You talked about these silicon factories where they punch out transistors. They cost huge amounts of money to build. What's the funding environment like for quantum at the moment? And do VCs understand that this is a long-term 10 or 20 or 50-year proposition and not something that are likely to see a return on in the very short term?
Yeah, that's a great question. So you're absolutely right. You can't build a million qubit fault-tolerant quantum computer on a shoestring. And, I think, again, there was some hope that we would access commercially valuable applications on a shoestring in this NISQ regime. And the jury is still out. That's still absolutely possible. But yeah, people are starting to recognize this is a big project to get it done. We've been very fortunate to raise a lot of money, and we're in a very privileged and very privileged position, and there's a lot of responsibility associated with that. But what that's allowed us to do, as you mentioned, is to go to one of the very few high volume chip manufacturing facilities on the planet, namely Global Foundries. And we're now able to build chips in that production line. And that's not cheap, relative to the experiments that I would do in the university. But it's paying off in a huge way as we see the reliability and the performance of these devices that we can uniquely access in those manufacturing lines. And so, yeah, we of course, I'm talking to investors I have been talking to investors on a regular basis over the last few years. And it's very, very encouraging, actually, the level of sophistication and appreciation that these guys have for the need for something that goes beyond a kind of MVP, proof of principle type system. So yeah, we've been very encouraged and, of course, very fortunate in that.
There's also a political angle to this, right? Not just in terms of manufacturing transistors and chips, but also in terms of the research and the prospect of one country maybe racing ahead with seeing China pouring billions into this, the EU is pouring billions into it, the US is pouring billions into it. What will it mean from a geopolitical perspective if one country kind of reaches the quantum peak first, or develops a technology that means that it can crack another country's encryption algorithms or can communicate without being spied on?
Yeah, I mean, I think the sort of example that I would point to is the semiconductor industry, which we, of course, deal with a lot. And in fact, recent news has made this more apparent than ever. We live in a really bizarre world where there are basically only 3 tier 1 semiconductor foundries that build the advanced chips that go into our laptops and cell phones. Those are TSMC, Global Foundries, and Samsung. Intel is a kind of a special case. But it's not like there's hundreds of companies or hundreds of factories that can build these advanced chips. And so the location around the world of those facilities is very important. And we're also seeing, um, you know, right now a huge problem with that global semiconductor device supply chain. That means that people are literally shutting down automotive production lines and stopping building cars, right? So, quantum computing, I think, is going in a similar direction. It's of course a very capital intensive and challenging technology to implement, and I think it's really important that we are conscious and careful about making sure that this technology is deployed in a sort of thoughtful fashion, globally speaking. Yeah, it's a serious prospect.
One of the big challenges that a lot of researchers in this field have had to grapple with, even in those small-scale experiences, is this increasing level of noise as you scale up. Can you tell me a bit about how PsiQuantum is dealing with that? If you want to build a 1,000,000-qubit quantum computer in a semiconductor factory, how do you make sure that it's not just undone by the noise that's coming off all these chips?
Yeah, so the transistors in your cell phone have an error rate something like 10 to the minus 15. So that's 0.0 followed by 15 noughts with a 1 after it, right? So they basically never have an error, and that's why your phone works reliably for years. The qubits, on the other hand, even our qubits, which we like very much, are still noisy, as you state. And the error rate that you're going to get is something like a fraction of a percent, realistically, from pretty much all approaches. And so if your devices are going wrong 1 in a few hundred times, maybe 1 in a few thousand times if you're lucky, the chance that you can run the billions of gates that we require for commercially valuable applications is nil, right? These things basically are swamped by noise within 10 or 100 operations or so in existing systems. And so there's kind of two approaches to solving that. One of them is to try to reduce that error rate a little bit and come up with really smart algorithms that allow you to get things done, before the machine falls over. And that's what people refer to as NISQ, or near-term intermediate scale quantum. And maybe we can find some super smart algorithm that's going to give us an answer before the machine is killed by these errors. Nobody's been successful in doing that yet. I've worked on these types of problems, and it's very challenging. What we're doing is really the kind of vanilla approach that has been understood, for more than a decade, which is to do error correction. So in your SSD in your laptop, on this phone call that we have right now, there's digital error correction running to deal with all of the errors that are happening, between you and me along this communication channel. And quantum error correction works pretty much the same way. You basically have, a bunch of information carriers that are representing the protected piece of information that you want. And if one of those goes wrong, you can kind of rely on the other ones to keep that quantum information. So this is something that I think the whole industry is increasingly understanding, that we're very likely to require error correction to do something worthwhile. And that's where this number of 1 million comes from, is that the best known quantum error correcting codes today require very large overhead, like a very large amount of redundancy, basically, in order for that error correcting code to work. So error correction really, as far as we're concerned, is the only way to build good enough qubits using these intrinsically noisy physical qubits that we expect to have. Yeah.
Given that, where do you think we'll be in 5 years or 10 years' time? When do you think we'll see real life applications for quantum?
Yeah. So again, there's still a chance that people will figure out a way to make these existing systems useful. So it's a huge scientific milestone that Google now has machines that win a race with a supercomputer. And that's an artificial race, but it's really showing the extreme power of a quantum computer. And it's absolutely conceivable that they'll figure out a way to do something useful and deliver on the promise with those types of systems. And I think I alluded to this early on. Yeah, if you try to build 1 million qubits with a science experiment type of technology and a science experiment type of mentality, yeah, that's going to take you decades, right? Like when I was in the lab building these systems, if you'd come and said to me 1 million qubits, I would say, sure, give me a few decades and I'll get back to you. Obviously, we're optimistic that by leveraging the incredible capability that people have built in the semiconductor industry, we can do that much faster. We are right now building quantum chips in these tier 1 production lines. That's a huge milestone for us. And so I think the sort of time frame that you describe is realistic. Of course, we're being very aggressive, and there's a lot that can go wrong. But I think that's realistic, to deliver real commercially valuable applications.
Great. We've got loads of questions from the audience. Thank you for sending those in. So I'm going to jump into those right now. We've got one about limiting factors. What do you think the limiting factor is going to be for this transition to quantum? Is it going to be hardware? Is it going to be algorithms? Or is it going to be skills?
That's a fantastic question. I think right now, nobody has working hardware, right? We're in this incredible position where there are small quantum systems, and even high school students can sign into some cloud provider and get access to a real quantum computer and run code on it. But that's very, very far from the big system that we ultimately require. So I would say this because we're building hardware, but I think, of course, we're not doing anything until we've got a working system, and we have to acknowledge that is a big challenge to get that thing up and running. On the algorithms and the software side, I think it's very important to make a distinction between algorithms and software. You can go on GitHub right now, and I would claim that you can download software, programming languages, compilers, etc., that are actually completely adequate today to program a working quantum computer, like a world-changing scale system. The software is in pretty good shape, in fact. The algorithms, on the other hand, we only know of a couple of them that are useful, and it's a very deep and creative mathematical task to find new algorithms. It's not something where we can just turn the crank. And so, I think that the world would benefit hugely from more smart people thinking about that algorithm discovery activity. But again, that's not going to stop us, right? Really, the hardware is the missing component as far as I'm concerned,
Another question from the audience. What kind of industries are you seeing interest in quantum from the most? Which industries, which organizations are investing in it the most? And are there any kind of surprising entities that are really in the quantum space that people might not expect?
Yeah, so we now work with a number of customers across automotive, aerospace, finance, healthcare, and we're working with them basically to prepare them for the existence of the machine. I think what's been surprising and exciting for me over the last 10 years of my career is to see how quickly these guys have got up to speed. 10 years ago, talking to a car company about quantum computing would be a little bit farcical, right? And now these guys have hired quantum information experts, and they're really smart and they're really organized about using this technology for whatever it is, battery chemistry, portfolio optimization, the usual suspects, right? And I think you asked about surprises. The other surprise, I'm a scientist. I'm a naturally kind of skeptical person, and very often we go and look at these use cases that potential customers are interested in. My tendency is to say, no, like this is not a good candidate for a quantum computer. You should just go use your regular computer for this one. This isn't in the right domain. And I've been, surprised and humbled a number of times when we actually go dig into these problems and realize, no, wow, there actually is a real argument for, meaningful speed ups from a quantum computer in this problem space. So that's been really, really gratifying, surprising, and exciting for me. Yeah.